lecture will be divided in two parts. The first part will be made on the blackboard, and it's similar to what you can expect for the following lecture, where I don't present material that are slides that you will have listened to at home on the video lecture, but I will make a question and answer and present some exercises. While doing the exercises, I may need some computer program, and so I will show also something on the screen. So this switching is always very delicate. So the second part, instead, I will go back to the slides that you have, to the PowerPoint slide, and I will present a number of videos illustrating different concepts of the program. So as a matter of introduction, we will conclude with some recap on the midterm, on the exams, and so on. Okay, so this is our plan. We may end before the 3 hours, which means that the rest could be used in principle to start looking at the next video lecture, which is calibration. This is included at the end of the 3 nominal hours of today. I will send through the Google group the exact amount of material that I expect you to look at, which will include calibration and one specific part of the next topic, which is redundancy, kinematic redundancy of manipulator. We will say a few words also illustrating a video today and the associated slide, and we will see each other next Wednesday, okay? So you will have the slot of Monday and some extra time together with the end of the slot of today and some small extra time to look at this material, okay? Any question on this organization, on the overall organization? Here in the room is clear. From home? So, one student is trying to speak up.
Can you hear me, Professor?
Okay. So, this means that I cannot hear you. I cannot hear you. No, I cannot hear you. Sorry. I don't know what it is. We will, let me see if there is some connection here that. I'm sorry. So take this into account. So I will look, I have on my computer the chat open. So from time to time, I will try to look at the chat and then reply. This is very inconvenient, but okay. So what do I want to do? So you can read this and I can cancel it, okay? I try to write big enough for these purposes. So I would like to make some example to start with of what we have mentioned while presenting the topics of the course. So after the advanced kinematic stuff, we have seen that the big block will be on dynamic modeling of robots. We have seen that dynamic model is, in fact, a mathematical tool that can be used then for simulating the robot on a computer, for computing the torque that the actuators need to produce in order to make a desired motion. So in a sense, for controlling the robot motion. In the model, there are several parameters that needs to be identified that can be written first symbolically, but then if you want to apply your model to a specific robot, you have to put numbers. And then there's a big chunk of lecture on the identification of these parameters, and then some extension How do you derive the model with the Lagrange or Euler technique, or with Newton-Euler technique, and so on and so on. But I won't enter into this now. I just want to make very simple example where we start asking ourselves, why do we need the dynamic model? What is useful for? Can we get rid of this in some cases? And in the background, and then I will make some block diagram also. In the background, keep always in mind that what we have done so far in Robotics 1, assuming that we can command kinematically the joint motion, so define, in the most simple case, a velocity. You can also modify it into a reference in position or in acceleration, depending if you integrate or go to a higher differential level, but without caring about all the dynamic aspect of the robot, which includes, as you can imagine, the masses, the inertia, the location of the center of masses, and other effects that modify the behavior of the robot itself. So keep in mind that we have, in that case, a low-level joint controller that is able to mask all these dynamic effects and let you command directly a velocity, and this velocity is what the robot is executing. But then we have to also say that this is not always the case. So with this in mind, there are also other considerations. So I will make my example mostly on our familiar 2R planar robot, okay, so that it's quite clear. So let's start with this. Suppose that this blackboard is not in the vertical plane, is a horizontal plane, so that gravity doesn't play a role. Why not? Why, when I'm moving in the horizontal plane, gravity is not, I mean, for a 2R robot, gravity does not play a role. Let's see if you have. So does this mean that the links do not have mass? No, of course. In fact, if I have a 2R robot which has 100 kilo for the first link, 100 kilo for the second link, and I have to move it, I need big motors, as opposed to the fact that I have 1 kilo and 1 kilo. Okay, so the mass is related to the gravity effect. But in the horizontal plane, what matters, and we will see this in very clear details, what matters is if the gravity field is producing work. So it's moving itself, the robot. While if you have a horizontal motion, so the joint axes are vertical, and of course the acceleration of gravity does not move the joint, okay? Instead, if you're placing yourself in a vertical plane, and then you have the masses where you apply the force of gravity, indeed this will fall. Okay, so we'll produce motion. So when we say that we are in the horizontal plane for a 2R robot, the joint axis has no effect on the joint axis motion by the acceleration of gravity. Okay, so we are in the plane, and suppose that we have our 2R robot like this. And now suppose that we are time 0 in a given configuration Q of 0, for instance, this one. How do we compute the configuration? We need a reference frame, okay? The Nerani-Tartenberg reference frame, or whatever set of coordinate definition you wish to have. So if you put here some x0 axis and some y0 axis, then you will have Q1 here and maybe Q2. These are exactly the θ1 and θ2 of the Nerani-Tartenberg. Okay, you can associate the frame, but we don't care too much here. Now, suppose that we have, first case, kinematic control, which means that we can command joint velocities, and these joint velocities are going to be executed if they are not too large. And for instance, suppose that we command q dot time t for some interval t, let's say, from 0 to capital T, let's say 1 second, 2 seconds, it's not relevant, this. Q dot of T1 is 0, and Q2 dot is, let's say, V2 positive. It's also constant, but positive. Okay? So it means that we are giving these references to a low-level control loop that tries to execute this. So how do you expect that the robot will move? So well, no reply, but I would expect that the first link remains where it is, okay, because I'm commanding no motion. While the second link will have a positive velocity. Remember, positive velocity means that the joint rotates in which counterclockwise, okay? So I'm expecting that this will do something like that. And when t finishes, all the commands goes to 0, and he has made a motion of this type, okay? Now, do we talk about masses here? Indeed, there will be a motor on joint 1 and a motor on joint 2 that will have to produce some torques in order to move this structure, okay? How much torque? Well, it depends if this skeleton of robots correspond to something which has heavy mass or small mass, and also how this mass is distributed, okay? So we don't know in advance and what will be the torque. And if we do this on a closed architecture, so something that we have bought and we can only command velocity, we don't know what are the limits. We may ask a large velocity, everything goes well, and even larger, all of a sudden, the actuators are not capable of producing that if the robot is heavy. If the robot is lightweight, then we can go beyond. So we don't have any idea of this because we don't have any dynamic model. However, for doing the same motion, you expect that there will be a larger demand of torque from the actuators if the robot is more massive, okay? So this is masked in a sense. Now, if you have to build your own robot, this becomes a big problem. Why? Even if you want to use a low-level control loop in order to command easily motion through the velocity command, then you have to size your actuators in advance. So once you have built the links and you know the masses, the inertia, and so on, you say, okay, if I want to go that fast or with that acceleration, my actuators that I have to buy and mount on my device, robotic device, how powerful should they be? Okay, and it's not a matter of kinematics, it's a matter of dynamics. Okay? Question on this? Second rotates, okay. Now, suppose that we have a second situation, and we say that we have a torque control. What does it mean? That we are able to command, and now we neglect all the details. Typically, we command currents to the electrical motor, sometimes voltages. But in a sense, we say, again, there's a low-level control loop on the actuators itself that we ask for a torque and the motor produces that torque. Okay? So we are commanding this robot with torque. So let's do again the picture. same initial configuration. Okay, almost the same. Okay, so this is x0, this is y0, q1 and q2 are the same as before. Okay, but now instead of saying I'm applying velocities or commanding velocities, we are saying we apply a torque tau1 of t and a torque tau2 of t with our motors. Okay? So if we look at this situation for an interval of time 0t, we say, for instance, something that mimic what we have done before. We say tau1 of t will always be 0, identically to 0. So no, the motor is turned off, produce no torque. And tau2 of t, let's say it's equal to t2 positive for a while. Okay? Now, what will be the motion of this? So this is a prediction now, just a guess. Let me see if somebody is asking. No gravity. Without gravity, we are still on the, let me write it here, no gravity. So horizontal plane, although I write it vertically, okay? So I mean, for special values of tau2, am I getting the same motion that I have here? Well, one may say, well, it depends on the dynamic characteristic of this arm. So suppose that we know this. And in particular, we know that the center of mass of the first link is somewhere here, let's say at the midpoint, but not necessarily. And we have a mass m1 here. Okay? Pay attention. The mass is distributed, but the center of mass is in a specific point. If you have a uniform distribution of masses and you have symmetry, geometric symmetry is at the center of the link. Okay? But in general, we need to know also how far is it, let's say DC1 is how far is the center of mass from the joint axis. The axis that moves this link. Same story for the second. Suppose that we have a mass m2 and the distance from its joint is dc2. You see, I need to put numbers there, but in principle, I can derive a model just with symbolic terms. Okay, and then at the end, I put the numbers. Because is this enough? Well, not really. Because if you take an object, for instance, this pointer, and this is an object, it could be part of a link of a robot, no? So if it's a link, I'm commanding the rotation of this object from one side. I have the motor here. But now, suppose that I'm holding the object, well, where is the center of mass here? Oops, more or less here. Huh? Well, it's too difficult. More or less at the center. Suppose that I'm rotating this object at the center, around the center of mass, so that the center of mass does not move. What is the other parameter which affects the motion of this mechanical object? Is its inertia. Because if all the mass is concentrated here, in fact, I'm not moving anything if it's a pointwise mass. The fact that the mass is distributed gives the inertia properties of this object. The more is largely distributed, for instance, the mass is very high at the end of this link, the more inertia this has, the more torque I need to apply to give the same acceleration. Okay? So another parameter in this very simple case, let me put it here, is the inertia I1 and the inertia I2, which are the inertia of these bodies of link 1 and link 2 around the center of mass. Now, when I'm rotating, of course, I'm rotating in the plane, so it's just one scalar. We will see that in general, if the body can rotate in 3D space, we need 3 numbers at least, because it's an inertia around the x-axis, the y-axis, and the z-axis. I may have inertias that are 3 by 3 matrices symmetric, but full, not diagonal. But in this case, these numbers are enough. So why I'm introducing this number? I'm introducing these numbers because, or these symbols, because I understand that depending on how much mass, how much inertia, how far are the center of mass from their joint axis, will make a difference when I'm applying the torque in what will be the motion, okay? In fact, if I know all this and I have a dynamic model, I can predict this motion. But now let's go back to our qualitative things. So my first question, to make it very close, is, will the first link move or not? I'm applying 0 torque, like I was commanding 0 velocity here. Well, in fact, it will. And this is the big difference between kinematic control and torque control. In kinematic control, you mask all interaction between the links. So as long as your actuators are capable of reproducing your command, the motion will be prescribed kinematically. So if I'm saying the first link has no velocity, the first link will not move. The fact that I'm saying that I'm not giving a torque, even if I start with 0 velocity, so everything is at rest, and now applying between this interval, no torque here and a constant positive torque on the second motor, well, typically, I will have this like this, but this may move also in the opposite direction. So this could be, it could be the final configuration. So you have an interacting motion. The second link will move, but also the first link will move. So the end effector will go, I don't know where, okay? It could go in the same direction. It could go opposite. This depends on many, many things. But if you have the mathematical model of the dynamics, you can exactly predict what will happen. You will integrate the differential equation of the model, and you get the result. In fact, this is what a simulator does. If you do this in Simulink or in Gazebo or in VREP, you get the motion according to this dynamic information. Okay? Any question on this? The first one moves exactly to conserve total robot angular momentum. The first one moves to conserve total momentum. Well, not really. Not really. I mean, this is more technical because by applying a non-zero torque, we are changing the total angular momentum. Okay? It's not like in situation like satellites in space or even astronauts. I don't know if you have ever seen those videos of the astronaut floating in space and moving their arms cyclically in order to change the orientation. They are exploiting the conservation of angular momentum in that case because they don't have gas jets to move around. All they have, these are conservative systems. While here, when I'm applying a torque, wherever I'm applying a torque with respect to the previous link, and the previous link is grounded on the floor, so I'm exchanging forces with the floor, so it's not a closed system. It's not a conservative system in general. This is a very technical question. I don't know if Riccardo Riglietti posed this question, but it's interesting, but it's not the case in this situation. Okay. So this reveals that there is a big difference between the two. And in fact, the non-interaction that you have when you command velocity here becomes in general a dynamic interaction. Not only when I switch off the velocity command, in this case, the robot stops. When I switch off the torque, the robot is in this configuration, but it may have some residual velocity, so it will continue to move. And if there is friction at the joint, like any physical system, real system has some friction, then it will stop because it dissipates energy. Okay, but after a while. Okay, so next example. Now let's put back gravity in the picture. By the way, once you have a dynamic model of this and you apply some form of torque, this is the most simple case. You can, of course, have sinusoidal torques or torques that increase like a seesaw, whatever. Then you integrate the model, the differential equation subject to these inputs, and you obtain the motion. And this is what we have called the direct dynamics. So we use the dynamic model for directly understanding what is the motion associated to some inputs. Okay, while the inverse dynamics, remember, is what are the inputs torque that I need to apply in order to produce a desired motion. Okay? So now, next example, let's take this robot and put it in the vertical plane. Okay? Suppose that now the robot is straight, is stretched in the horizontal position, and there's gravity, G0, 9.81 meter per second square as acceleration. And who feels the acceleration in these links? Of course, the two masses, M1 and M2. And it depends on where they are located on the link. So on these two dynamic parameters, which specify where the center of mass is on the link. Okay? Now, suppose that tau 1 and tau 2 are 0. So everything is switched off. And the robot is at rest. So you're holding the robot, and then you release it. What will happen? It will fall down. How it will fall down? Well, sometimes you can do this simulation. This starts to be chaotic, because depending on how the masses are there, you can have a continuous fall or a jump like this and some bouncing back. It's very interesting, by the way. It's not what we would like to do with robots, of course. Maybe with jugglers or some type of strange object. But now let's put this, so we have said this will fall. Typically, both will go down at the beginning and will acquire some velocity and go down. Now, suppose that I'm starting with this configuration. So Q1 is equal to Q2 times 0 is equal to 0. If this is x0 and this is y0, these are exactly the configuration of the Denavit-Artenberg theta angles. Okay, so I'm starting stretched like this. But this is not enough when we are dealing with dynamics, because the motion will depend also on the initial velocity. So if we suppose that Q1 dot at time 0 and Q2 dot at time 0 are 0, so the robot is at rest, although somebody should keep it in this configuration. For instance, you from the outside, otherwise it will fall. But if you start from this, then it will fall. It will fall, so both joints will move clockwise. Okay? So this will go down, and this will go down, maybe. The first one is certain. The second is... So now I modify a little bit this, and I write that the first joint has 0 velocity, and the second joint has a positive velocity at time 0. So you like taking a picture, the robot is straight like this. This is not moving, but this is having an instantaneous velocity going up. Okay? Now the question is, if I start from this state and I don't apply any torque, will the robot go up or fall? In particular, I'm interested. So if I'm saying that here, Q dot 2 at time 0 is positive, my question is, will this go up or down? The second will go up. Somebody says the second will go up. What do you say? Will go up. Certainly. Not certain. It depends. First, how large is this velocity? If it's very large, well, before gravity will stop this motion and then reverse it and bring it down, it will take a while. So the first instantaneous motion will be going up. But this depends on the intensity of the initial velocity and on the mass of this stuff. Okay? If you have a large mass here, well, it starts, and in particular, if it's the center of mass is placed quite close to the tip, then this will eventually fall down if the initial velocity is not large enough. You see, all these questions are consequence of an analysis. If you have the dynamic model, you can compute what happens exactly. Okay, while in kinematics, nothing can be said at all. Okay, so next example, let's cancel all this. Again, we will consider a 2-hour robot in the vertical plane, so like on this. Okay, again, so this one. So the next example is the following. So we have, again, our good old friend. He will start in some configuration. Let's put the second link below. And so suppose that we have a certain initial configuration at time 0. So the parenthesis stands for time. And this configuration, let's call it Q0. And suppose also that Q dot at time 0 is 0. So the robot is at rest at the beginning. Okay? And now, let's look at the position P. So we have, again, Q1, we have Q2, and we can compute through the direct kinematics the position of the end effector. And we are not interested in orientation, so this is a problem where we want to control 2 Cartesian quantities, Px and Py, with our the motion of the 2 joints. So there is no redundancy. Things are pretty much, as long as we remain inside the workspace and we don't go into singularity. Now, suppose that we assign a motion. Well, maybe this is too far away. Okay, let's do a smaller motion, like a circuit. We want to move with a p desired of time along this path. So we give a trajectory in the Cartesian space. We are in the initial point. So suppose that p of 0 is equal to P desired times 0. So the end effector is placed where it should be at the initial time of the trajectory. So we don't need feedback in order to recover some error. Of course, if I'm placing far away, I see an error. And you should remember that if I'm doing Cartesian kinematic control, I can command the joint velocities in such a way that I recover the Cartesian error and then track exactly from some time the desired Cartesian motion, okay? Again, now I'm skipping this. We know that. We know how to do. We have to invert the Jacobian in real time in that case. But here, we have also the dynamics to take into account. First of all, so we go back to this initial matching. And we are saying, who's holding the robot in this configuration? I mean, you start this motion at time 0, but time 0 may be 3 o'clock. So until 3 o'clock, who's holding the robot there? Because otherwise, we are under gravity, so remember, otherwise this would fall. So I need to apply, I mean, my actuators, even if the robot is not doing anything, should produce torque in order to compensate gravity in that configuration. Okay, so for sure, I will have some tau1 of 0 and tau2 of 0 being applied in order to stay at rest in the initial configuration. So if I stay for long enough, and these are electrical motor, what will happen if after 2 hours, 3 hours, 4 hours of this? What do you think? Overheat. Okay? So this is one reason why, if we have very heavy structures doing pick and place operation of big chunks, but then holding this payload in a fixed position for quite a long time, because of the power and because of the absence of heating, in that application, people used to prefer hydraulic actuation instead of electrical actuation, because a hydraulic actuator closing the chamber in pressure doesn't produce any work for sustaining the load, while an electrical motor should continue to rotate to generate torque and sustain the robot and the payload that the robot may hold in that configuration. Okay, so you see, again, this is a matter of dynamics. How much torque do I have to produce? Kinematics tells me nothing, because by kinematics I would say, okay, I want to stay here. I command 0 velocity for the first joint, 0 velocity for the second joint, and this should stay there. But I miss the whole production of torque. It's embedded somewhere, but the actuators are producing torque, even if there's no motion. Okay? Now, then the trajectory starts. So this is for t in some interval, 0, let's say infinity, so I cannot close. It means that I'm going on and on and on. Okay. Now I'm saying, if I would like to solve the problem from a motion planning, so from a kinematic point of view, what would be the command that I have to apply, the velocity that I have to apply here? I should do the inversion of the Jacobian. So I will have to compute P dot. So typically I will command Q dot desired as j to the -1 of Q desired of t times P dot desired of t. So I will look at the speed that I will have a profile that will start with 0 velocity and then increases. So I will slow down at the corner, then accelerate here, then slow down, and so on and so on. Okay? So I have a profile for P dot. I have the initial configuration Q. I generate a velocity. And then if I'm doing this in simulation, I'm integrating the velocity so I know the next configuration, and then I repeat, I cycle all the time. Okay? You can do this in Simulink, for instance. It's very simple. This would be an inversion of a Cartesian trajectory generating a joint trajectory with joint velocity commands without knowing in advance which will be this trajectory. Okay? We only hope that while doing this path, in fact, I reduced the path on purpose, I will not stretch the arm. Otherwise, in singularity, this inversion creates problem, as we know. Even close to singularity, it creates problem because it will request very large joint velocity that the actuators, again, are not capable to produce. Okay? But this is an old story. Now, what if now we have the dynamics and we would like to command torques? Well, this is an inverse dynamics problem. So this is given P desired of T, we can associate a desired Q d of T, and then also a Q dot desired, and also an acceleration. And we will see why is this. But if I have a motion in configuration, I can also take out the values of velocity and acceleration. And then we compute tau desired of T. Now, this is a vector with two components, tau 1 and tau 2, in this case. And this will be some function of Q desired, Q dot desired, and Q double dot desired. And this, here, you have the dynamic model. It enters into this function that we don't know yet the form that it has, but we can derive exactly this function for any robot with any number of joints of any type, with any distribution of mass, inertia, and so on. You can do this in a very general fashion. So here what we have computed, given a desired motion, here in the Cartesian space, but it could have been directly defined in the joint space. So the inversion between Cartesian and joint space is still a kinematic issue because it involves Jacobian and direct kinematics and inverse kinematics. But from there on, it becomes a dynamic problem because this function will be a function also of the masses, of the inertia of the center of the position of the center of masses, and so on. Okay, so we are solving here what we have defined as an inverse dynamics given a motion, compute the torque that will produce that motion. Okay? Any question on this? No question from home. So let's move to next example. Okay? Now, again, take our robot. I don't care if it's in the vertical or horizontal plane now, but suppose that it is in contact with a rigid surface. So the end effector is touching this surface. It cannot penetrate the surface because this is stiff enough. Also, the robot is stiff, but let's say they are equally stiff, so really nobody wants to comply. So can we move, supposing that we don't want to leave the surface? Because if we leave the surface, then the robot is free to move anywhere. But we want to keep contact. Can we move in any direction in the plane? No. The only direction where you can move while keeping contact is this one, either along the tangent, either in one direction or the other. So we can, this is the V desired that we can have. We cannot enter the surface because the surface is infinitely stiff. We cannot leave the surface. In practice, we won't, but then we would change the type of contact. For instance, the end effector has a tool which is removing some extra material from a metallic part. So it's clear that I don't want to move it away. So if I have only one scalar, this VD can be seen as a scalar in this direction. So I may move very fast or not, or stay still. I could only not move this. And I have two joints and two commands for controlling one quantity. So apparently I have a redundancy. I have more commands than I need to do some tasks. Is this correct or not, this way of reasoning? What is missing here? Let's see if somebody, in this example, when did we compensate for G acceleration? I think that he refers, Riglietti refers to the previous example or to this example with the contact force. With a force applied to a surface. Well, again, we have not yet said what we do with gravity. So what is missing in this picture? What can you do when you are in contact with the surface? Not only move along the tangent to the surface, but also apply some force. So in fact, I can also apply some force Ft. Of course, this should be a positive quantity, because if I apply a force in the other direction, the environment will not react and will let you go. The environment reacts only if you're trying to enter to it, so applying a force for entering, okay? So this is a difference between here. Here I can go in one direction or the other, but here I can only apply force positive or zero, not negative force, okay? Now, if I'm not moving, so Vd is equal to 0, and I want to apply a force Fd along this direction, which is the normal to the surface. Of course, the surface may also be not linear, but this, as long as we don't move, doesn't make any change. Along the normal, I would like to apply an Fd, so it's the same situation. So how do I apply this force with my actuators? So I'm saying Vd is equal to 0. What torques should I apply? You remember? J transpose, correct. JD, tau d is J transpose of the current configuration, let's say Q0, times Fd, which, however, should be a vector. So pay attention. This is a scalar, but is associated to a direction. So with respect to a base frame, this is, in fact, Fdx, Fdy. Okay? The Jacobian is square. This is not a singular situation. So we know that in static condition, you remember that? Static transformation of forces, in order to apply a force without moving, and in particular without moving on the tangent, I need to apply tau1 desired and tau2 desired here. Do I need dynamic information for doing this? Do I need to know if there is gravity, how heavy is the robot, and so on, the inertia? In fact, no. In fact, we have done it already in kinematic, in Robotics 1. And the Jacobian is a kinematic quantity. It has nothing to do with distribution of mass. So now the question that was made at home comes into play. Well, if this is in the horizontal plane, then we don't need any information about the dynamics. But if it's in the vertical plane, even if it's not moving, so the robot is not having any velocity, no acceleration, so here this is 0, this is 0, the only thing that matters is which configuration the robot has. In fact, this configuration is the initial one because we don't move, and this is a kinematic quantity. But if there is gravity, this robot would fall under gravity. So in order to stay there, it's like at the beginning of that other motion, we need at least the torque that compensates for gravity so that I can stay there, and then I can decide to push. So in addition to this torque, you will have a term, let's call it G of the configuration that you have. So the total torque will be compensating for gravity so that this becomes the system like if it was on the horizontal plane, because I'm sustaining it in that configuration. And then the rest is purely kinematic. If instead this moves in the this stays at rest in a horizontal plane, this term is gone and it's a purely kinematic transformation. Okay. However, what happens if FD VD is different from 0? Well, now things changes. So I can go fast while applying forces. So I have a hybrid task, in fact, here. I'm trying to control the contact forces along the instantaneous normal. This is always the same direction if this is a linear surface. But if it's a curved surface, the normal changes, and also the tangent changes in orientation. So everything is changing. So I have a task where I'm trying to command motion on some surface while applying force constant or time varying on the normal. And I'm moving the robot, and if I'm moving the robot and I want to command torques, I need to know how heavy is the robot, what is the inertia of the link, and so on. So the dynamics comes fully into play. So when we interact with the environment, and this is the conclusion of this example, if we are doing things statically and in the absence of gravity, because of the configuration or because of some compensation of gravity, then this is still a purely kinematic problem. If we are moving in contact, then this is, again, a dynamic problem where we need the dynamic model. Okay? Any question from home? No. Okay. Now, what's left? There's a final example, and then we are done with this part. And the final example has nothing to do with, I mean, I make a simpler one. So I'm not showing a robot, even a simple robot. I'm just showing a mass, a single mass, or maybe multiple. Let's see. So just to say that a final need for dynamics, it seems strange to say, but is when you have to include phenomena which are intrinsically dynamics. And I will mention only two. Friction. Friction is related to motion. And it's related to the nature of the contact surfaces, to how much I'm pressing on top of a surface, and so on. And flexible phenomena, deformation phenomena. If you studied correctly actuation and transmission element, you should remember that there are the first point in an industrial robot, or even in a lightweight collaborative robot, which is on purpose designed for this reason, the first place where some deformation may occur is where? You remember that? So if we have heavy, consider the industrial case with rigid links, massive. In fact, they are rigid and massive. They're massive because they want to be rigid in order to be very accurate in positioning and not having any deformation despite you apply large forces on the workpiece or on the environment. So the links are rigid, but typically there's a point where you have some deformation, and these are the transmission at the joints. Sometimes you use belts to displace the motion of a motor to the joint, so that you don't have to carry also the motor. So the motor is at the base, but you have to move the second joint. So you have a belt going there, and a belt is elastic. So if you give too much torque, it will slightly deform. So the position of the motor is not longer one-to-one related to the position of the link. Or you have harmonic drives, which are intrinsically flexible. There's a flex spline. So you guarantee a large reduction ratio, which is associated also to a large amplification of the torque produced by the motor. So the motor has limited torque, but after a reduction ratio of 100, 160, which are the numbers that you can achieve with a harmonic drive, then the torque that is applied to the links after the transmission is amplified by 100, 160, and so on. Okay? So you can accelerate much more. So all these phenomena are nonsense if we stick with kinematics only. And we will see this with this simple example. So suppose that you have a single mass M moving on a horizontal surface, no gravity, okay? Now, where is this located? Somewhere. We need some reference frame. Let's see that wherever it is, the position of this mass, we call this position Q. Why Q and not X? Because Q reminds us of a joint variable, no? So this is, and suppose that we have a force input applied to this. So with this force, we can move, the positive direction is this, but the force can pull and push. So it can move this mass in one direction or the other. Okay? However, this is in contact with the surface. You can have a metallic part moving on wood, or you can have an object with rolling, with wheels on the surface. So depending on the type of contact, rolling or sliding, and the nature of the materials, there will be a friction, which always opposes motion. Remember, friction is something that works against motion. If you don't move, you don't have friction in general. Sometimes you have a special phenomenon which is called stiction, which means that if I have a sticky surface and I'm not moving, and I'm applying a force, I apply a small force, nothing happens. Why? Because stiction holds the parts in place. Only if I overcome the amount of stiction, then all of a sudden the mass will start moving, and the stiction effect is no longer there. So suppose that you apply 1 Newton, nothing happens. 2 Newtons, nothing happens. 3 Newtons, so you overcome a stiction which is, let's say, 2.5 Newton. Now, as soon as the mass starts moving, you don't see only the 3 minus 2.5 Newton. You see the whole 3 Newtons because the stiction is no longer there. You will see another type of friction. And for instance, we suppose that there is a F friction here, also function of time and of speed and of many other things. But we will suppose that this is more or less Kf times Q dot, and this is what is called viscous friction. So you have a force which opposes motion. In fact, you see that it's in the opposite direction of the positive Q. So if you have a Q dot there, then you will have a force opposing in the other direction. Okay? If you're not moving, this goes to 0. And it's a linear effect. So it's a simple model of this dynamic phenomena, which is hugely complex in general. So if we want to write the dynamics of this object, this is an exercise of physics 1, I would say. How do we write the dynamic equation of this mass, subject to forces? We use Newton's law. Sum of the forces applied to the mass is equal to the mass times its acceleration. Correct? So let's write it like this. M, the mass, times x acceleration, q double dot, is equal to the applied forces are the one that comes from the outside, our control force, the input F, but then minus F friction. Okay? And you can see that if I'm applying a force and there were no friction, this would transfer totally into an acceleration of our system. But because of friction, something is taken away from my force. I'm losing something. Always opposite to the direction in which I would like to move my mass. So if we are assuming that the model of viscous friction is this, then I write F minus K friction viscous, okay, times Q dot, okay? And since this is an equation, I can move terms around. I can bring this term to the other side. So I can rewrite this as M Q double dot plus KF Q dot equal to F. And this is a differential equation of the second order because they are the second derivative of the variable Q, which we don't know in advance. It depends. We have to integrate this differential equation in order to get motion out of a given profile of input force. So again, we are solving a direct dynamics problem. This is the model. In order to know how the mass moves when we apply a force, we have to integrate this differential equation. Okay? When you integrate differential equation, you have to know the initial condition. What are the initial conditions for this second order differential equation? Well, it's not said that it's equal to 0. First, we should know where it is the mass at some point. So I need to know where I'm starting from, Q0. It could be 0. I could say, okay, where I am is my 0 position. And then from there I count. And this is typical with encoders. No? You know, incremental encoders does exactly this. You locate the 0, and from there you count. Okay? Then you map this into the kinematics. So this is, but not only this, we need also the velocity at time 0. We may start with 0 velocity or not. And depending on the velocity, and not only on the position, the mass will have a different evolution, even if we are applying the same story of input. So this is, in fact, the full state. Remember, those of you who have studied some system theory, the state of a system is everything you should know at the given time in order to predict what will happen to the system when you know the inputs to the system from that time on. So the state collects all the past history. You don't need to know from where this mass is coming. If you know the state at a given instant, what was the past is gone. And all the information is in the state. And for this second order differential equation, so for mechanical system, you need to know position and velocity. Otherwise, you cannot say where this will go. Now, what is the specific nature of this second-order differential equation? Can you see it? Now you have to remember calculus. So where you studied differential equation, and typically you have studied differential equation with constant coefficients. So-called linear differential equation. This is a linear dynamics. And not linear because I'm moving along a line. It's the same would be true if I'm rotating an inertia with a torque instead of pushing a mass along the line. It's linear because the principle of superposition holds. And in fact, we have a closed form solution for this. We don't need to, I mean, we can integrate this numerically with some simulator, with some algorithm for integrating the differential equation, but we have a closed form solution for this, with an integral of convolution and so on and so on, something that you study in system theory. Now, this is one property. The other property is that these two numbers, or these two symbols, if I put numbers there, can I put any number there? Or there is some restriction, some physical restriction? They are both positive. There's no sense of having negative masses. Maybe in quantum physics, this may be not true, but in macroscopic physics is correct. And this, because of the fact that this opposite motion should be a positive coefficient. Okay, so both coefficients are positive, sorry. So this is positive, and this is positive. Now, big jump, I'm requesting. So suppose that we are at some instant, let's call this not zero, let's call it t bar, and we have some position and some velocity. Okay, and from there on, we switch off our input. So the mass is somewhere, it has some velocity, positive or negative. I don't apply any force. What will happen? Will the mass continue to move at the same velocity? It will reverse velocity. It will stop. It will stop after a while. What do you think? Let's see if from home I have some suggestions. Okay. Okay, so very good. I will tell you what your colleagues are saying from home. The velocity will decrease, and then the system will stop without oscillation, I would add, because of friction. If there were no friction, then we would have mq double dot equals 0. So q double dot is equal 0. So there's no acceleration. So I will keep on going with the same velocity forever. But because of the friction, the velocity will exponentially go to 0. And the exponential constant will be exactly the ratio of kf over m. So the solution of this differential equation is, let's say, from t minus t bar, so for all future instants, is exponentially, it's q dot at time t exponential of minus kf over m times t minus t bar. And because of these two numbers are positive, the coefficient is negative, and this exponential will go to 0. And the velocity will go to 0. Of course, if you integrate this, you will understand that if at time t bar you were in some position, you end up stopping with the final position, which depends on how this velocity is going to 0. Okay? So you see, you can really use the model to predict many physical aspects. But you will not predict any of this aspect if you're just saying, okay, I'm commanding a velocity, then I stop. It's correct if I had a low-level loop that receives this as a command and then applies a force such that. But you miss all the dynamics in this way. So when you have friction, you see that dynamics, only through the dynamics you can take into account friction. The fact that you have friction or not, it has a completely different behavior. Okay? The other effect, as I was saying, is the following one. Suppose now that this mass, which we will see is surprisingly, you have seen multi-degrees of freedom manipulators. If you can imagine how the mass is distributed there with inertia, is very complex. But through control, so commanding the torque in a proper way, which is based on the model that you have, you may let the robot behave in any direction in the joint space or in the Cartesian space as an elementary mass like this. So this is one direction. So you can have the end effector of the robot moving as if it was a mass, let's say, of 1 kilogram in that direction and in the other direction. Or you can say, in that direction, I would like to see 10 kilograms. In that direction, I would like to see 1 kilogram, and so on. So you can replace the complex nonlinear dynamics with a very simple model like this. Okay? And it's not an approximation. It's because the control law is very smart and is compensating for all this effect that you were able to model. So, again, back to this simple 1 degree of freedom system. But suppose that between the point where you're applying the force and the mass that you would like to move, there is some elasticity. How do you model this? Well, you split the mass in one part, then you put a spring, and then you have the other mass here. Okay, and of course, M1 plus M2 will be equal to M. No? So you're saying that here is everything is rigid, it's only one body. But in fact, I'm pushing with my F on the first body, but I'm not moving instantaneously the second one because there's a spring in between, which is elasticity. Of course, if the spring is very stiff, is infinitely stiff, then these two masses are rigidly moving together and they move exactly like this. But because of a finite stiffness of the spring, which would be the compliance of a transmission like a belt or something like that, then the position of this mass and the position of this mass are different, not only because of this offset. So I can call this again Q because I'm interested in controlling the position of this. And I will call this as theta. Okay, and this will be a Ks, the stiffness of the spring. Suppose now, forget about friction. And now the question is, can we model this system? Can we model the presence of a deformation? The deformation is not a kinematic effect. It depends on how much force I'm applying, on how stiff is the spring, what are the masses on the two other sides. Okay? So it's a purely dynamic effect. Again, cannot be captured by kinematics. Can we write the equation here? Now, first of all, we're supposed to remain in the linear domain, so where all phenomena satisfy the principle of superposition of effects. We suppose that the linear spring is in its linear domain. This is an elastic spring, so it generates a force which is proportional to the deformation, and the coefficient of proportion is this. So we have an F spring, which is Ks times Q minus theta. Okay? So, well, let's write it in the other way. We will see why, but you can choose whatever. Okay. So when theta is equal to Q, so the spring is not compressed and not extended, it does not react with any force. Only if you compress the spring or you extend the spring, you have a force which brings you back to the neutral position, which is when the two masses have the same position. Don't be disguised by the fact that I'm computing theta here and here, so I have a displacement. You can also always redefine things that this, when the spring is not compressed, I have the 0 for this and the 0 for that, okay? So really the different matters. The different gives you the compression or deformation of the transmission. Okay, so now if you look, you have to write two differential equations, one for every mass. Remember, this is a general rule. So you can imagine that if you look at this mass, you have a force applied as an input force and a force applied here due to the elasticity, okay? So let's call this f of s. And of course, on the second mass, you have a force only coming from the elastic effect. And because this is a spring and the principle of action and reaction, if the spring is pulling one mass toward the rest position, it's pulling in the other direction by the same amount the other mass. Okay, in fact, this depends only on the stiffness of the spring, not on the value of the masses. Okay? And you have the same force applied here and here, but in opposite direction. So if you imagine to take the two masses which are in the rest position and bring it by hand far apart, the elastic spring will tend to bring back the masses in this direction. And similarly, if you're pushing together, the spring will react in the direction, but always by the same amount in the opposite direction. And this is very important. So I will give you the final result of this. If I do Newton law for this mass, I will have mass 1 times the acceleration of this mass is t double dot equals sum of forces applied, the input F, and then minus F of S. And same story here, the mass 2 accelerate with Q double dot. What are the sum of forces applying here? Not this force, because this is applied to a different body. Here, the only force is Fs. So I will have Fs here. Correct, I wrote the things in the right way. And now I have two differential equations of second order. Are they linear or not? Still linear, because only constant coefficient here. Okay, if I write it more explicitly, this is F minus Ks theta minus Q, and this is Ks theta minus Q. Okay, and you see that there is some coupling. You cannot solve this equation without having solved the second. Why? Because this is theta double dot. It has a theta, but it has also a Q. And the Q comes from the solution of the second equation. But if you look at the second equation, in order to find the solution of Q over time, you need to know the theta. So they are really coupled together. And the coupling is exactly the elasticity. Okay, still it's a linear, it's a set of two second order linear differential equations. You can solve it in closed form if you wish. You have a special integral once you know which force you're applying. Okay, so I would make a stop right now, and then we switch, make a break of 10 minutes, and then we switch to the video part, which is not so intensive, it's more enjoyable, I hope so. You have any question here in the room or from home? No. Okay, so it's 3:25. At 3:35 we will resume.